Thank you. Yeah, so thank you for the introduction, and to Professor Tiki, because he's laid out the nomenclature for my talk, so my talk is very short today. Today I'm going to talk about the latest release, which just, came out last week. For details on the formulations that are implemented, you can see our publication from last year. The Bitbucket workspace includes the initial data code as well as the forms that I'll talk about later. And there's actually my talk from last year, which I'll actually reference during this, that you can also watch on YouTube.
10 minutes.
You can ignore the demo, thankfully. Okay, so what is FUKA? FUKA is a suite of initial data solvers focused on extremal binaries. So highly asymmetric, highly spinning binaries. It can be binary black holes, neutron stars, or mixed binaries. It solves the XCTS system of equation, as Professor Tiki discussed. The black holes are done using excision, and the neutron stars can be constructed using either polytropic or tabulated equations of state. Excuse me. There's also the ability to do eccentricity reduction procedures, either using post-Newtonian or iterative means. So I actually stole this from my talk last year. So FUKA v2 is actually what I said was going to be done. So this is a transition to using boosted isolated solutions to generate the initial setup for solving your binary initial data. V2 is a complete rewrite from V1, so that's why I say V1 is essentially deprecated, but it's more easy to read. Whereas V2 is a more abstractified version. It's a systems integration problem. We haven't finished superimposed care shield. This is work in progress, but unfortunately it's not done yet. Obviously, the solvers have been drastically improved in order to make this possible. And improving documentation is always an ongoing process, but I've done my best to make a positive step forward. So when considering binaries, we want to look at a system, either something that's been observed or maybe will be observed, and astronomers get to look at nice pictures, but we work on computers, so we need something that's more easy to work with. So this is our pretty picture, where we have two components with two different masses and a given separation. Obviously, we need to have some sort of a coordinate system for this. So we have kind of the measurement, the binary frame, as well as the local frames on the two objects. And we have two different masses to specify. So in the case of a black hole, we have the Chrysodual mass, which incorporates the irreducible and the spin component to give you a total gravitational mass. And for the neutron star, you always read about it in literature as the gravitational mass at infinite separation. In our case, we just solved the star separately, and so it's our ADM mass in isolation. From this alone, we can already kind of make some initial guesses as to what the solution is going to look like. So as Professor Tiki had mentioned, we have to have some sort of a helical killing vector that approximates a stationary spacetime. In our case, since you have asymmetry, you have to shift
5 minutes.
And in our case, we actually just use the Newtonian center of mass estimate, which actually proves to be pretty good in most cases. But you need the center of mass estimate in order to do a PN estimate for the orbital velocity. So that's why the center of mass is important. And with that, now we have an idea of what this omega is going to be. To give you a total picture of what the binary will look like in the end, you also have these local orbital velocities on the objects themselves. These are defined, or these are fixed using whatever input spin. This is predominantly done by this dimensionless spin parameter, which is the spin angular momentum normalized by the mass squared. And the spin angular momentum is the surface integral. For a black hole, this is done on the excision surface. For the neutron star, this is done somewhere outside of the neutron star surface. And these spin parameters show up in the equations in terms of boundary conditions. So in the case of a black hole, you have this boundary condition on the shift, the tangential component of the shift. In the case of the neutron star, this is in the specific enthalpy current decomposition, where you have a divergence free term plus some rotation term. Now with this information in mind, we can actually solve this stuff independently. So we have our black hole, we have our neutron star, we solve it for a given mass and a given spin, and then we can boost it. Well, we boost it with this omega guess that we had gotten from the 3.5 PN estimates. And what you can actually see once you actually solve the boosted one and the binary is that this omega and the boosted TOV or boosted black hole solution is actually very close to what you will actually see in the binary solution. And the point of this is that you want to get a solution that is similar, but obviously is going to be different because you don't have the component or the companion to influence the solution. But it's close enough that it gives you a very, very good initial guess. And so now that we have our boosted isolated solutions, we can now do what's called the superimposed aspect of this, which is you take your background. So in the case, this is lapse, the background when in flat space-time, the lapse is 1. You have this decay parameter, which I've just said is kappa. This is not normal, this is just to fit on a slide. And this kappa term is an exponential decay that's a function of the coordinate radius from where the components are in the binary, divided by this weighting parameter, which we said is the separation divided by 2. I think the first time I saw this was in FUKA's paper on black hole neutron star binaries for superimposed Kerr-Shield. But essentially you do this for each field, and this constructs your initial setup for your binary. So why do this? So one, this is the initial guess for the binary setup reduces the computational cost by getting to the solution more efficiently. So we actually see up to a 4 times speed up, just getting the binary initial data, depending on which setup you're looking at. And we're also reliably able to do closer separation distances without any issue because the setup is so, I would say, accurate. This 4 plus n, so for anybody who's familiar with the original solvers, to get to like highly asymmetric or highly spinning binary configurations, you had to do incremental solutions manually, which is now done automatically. And so this is where the 4 plus n comes from. And all of this can now be done
1 minute, please
automatically. So there's a single config file, there's a single solver for each of the binaries. The user can set up everything ahead of time, and then everything is done in the background. So my summary, FUKA v2 is FUKA just does it better and faster. All these efficiencies come from building the initial setup in a more appropriate manner, and obviously computing isolated solutions is much faster than doing, I would say, expensive iterative steps in the binary space itself. It does this by using the superimposed boosted solutions. You can do the eccentricity reductions, and more importantly, for anybody interested to try this out, you can see our workspace or talk to me if you have a different evolution code that you would like to get this to work. Thank you.
Thank you, Samuel. Roland, you kept the time. Are we out of time for questions?
We have 1 minute.
We have 1 minute. Okay.
The next speaker should start.
Yeah, please. So while I set up for the next speaker, any questions in the room or online? Leo, could you shout it out if there is one? I want to get set up.
Yeah, so you said you have a 4 times increase in efficiency. So what's the actual wait time now?
Yeah, so I say up to 4 times because, like in the case of the binary black hole, there was a lot of stages that was required because you built the binary from flat space, and it required 5 stages, like 5 different solving stages to build up that solution. In the case of the BNS, there was a couple of intermediate stages. In the case of the BHNS, it was very sensitive, and you had to solve the BNS first. So I would say overall, most things are done, I would say, for low resolution, depending on how you compiled the codes. I found this out recently. Within a couple of hours, I would say on a single node with 120 cores. But to go up to the resolution, this obviously takes more. The nice thing about KADATH is that it scales to many cores very easily. And so if you have a small cluster, you can scale it up very, very easily.